Okay, guys, can you hear me? So, if I'm not wrong, I think next week we are all off because of spring break, and that means that this week is a week where you guys need to pick a project, or at least by the end of spring break. So let me just put out a reminder that it's time to pick a project, and you can just email me your choice. So I want to ask if there are any questions related to this part. We talked about the projects, I think last time. Some of you picked and some of you have not picked yet. So there are projects on fixed income, there are projects on equity, there are projects on default securities, and then there are some projects on predatory trading. This is more like a research area than it is it's also very practical, but the papers that I have listed, they are definitely academic papers. Okay, so think about it and let me know, just send me an email. And then today, what I had in mind is we're going to be looking at these stochastic wall models. So the main ones will be Heston. This is by far the most popular one. And the other one we're going to be looking at is Stein and Stein. Right, and this is where this is where we need characteristic functions. That we spent so much time talking about. So this is going to be like the first part. I'll take you through some of all the calculations. In many ways, they're similar to the calculations we did last time. We talked a lot about replication last time. What we'll see here with the characteristic functions is quite similar. Applying Ito's lemma, looking for a martingale, and so on. But we'll see that in more detail. And then I'm hoping after the break, we will switch over and we talk about copulus. So these are what is the main model of default modeling. So these are jumps. How do you create models that have a jump in them? And I should say here that you should see notes on Canvas about this. Okay, so let me start by pulling up the homework that is related to Heston and Stein's model. So let me share a screen. And so if you go into homework, there should be a homework number 4. This one, no. And this homework here, this is all about implementing Stein and Heston's model. So the first problem is about Stein and Stein. So it's a stochastic Wald model. So you implement Stein and Stein. And then the second problem, this is when you start calibrating. So in the second model, you're going to be playing with Black-Scholes. And you're going to try to figure out what the implied volatility is so that the Black-Scholes model coincides with this stochastic Wald model of Heston and Heston. And then the last part is you switch over to the most popular one. This is Heston's. And Heston's model has there's a reason why you might prefer Heston over Stein and Stein. Heston's model is available in closed form. Everything has explicit solutions. Stein and Stein does not. And so that might be one reason why one would prefer Heston over Stein and Stein. And so the last exercise asks you to calibrate the Heston model to this Stein and Stein. So that's what it says here. In this exercise, we'll take Stein and Stein's model as being the real world model, and then you try to fit a Heston's model to it. And so that's the next homework. And this is it looks excessive. It looks like it's a lot, but it's really the first problem. Getting the first problem correct, then the last problem is going to be a small variation of the first problem. Okay, so what I'm going to start by doing is talking about these stochastic volatility models and go over some of the things that you would need to do in this homework number 4. Okay, so let's get started on that. We have we have an equity model. Equity models to say that the interest rate is equal to 0. This is just for simplicity. So we're going to start with that, and then we're going to say that there is one risky security. So you have your DST as the form ST sigma T dBT, and the initial value is something positive. Right, so recall this is an SCE, right? And S appears on the right-hand side. So you have, it's an SCE because S is both here and S is over here, and it is this sigma. Right, so recall that you can use Ito's lemma. That Ito's lemma shows that ST, you take the initial value and then it's an exponential because it's linear and S on the right-hand side, so it's an exponential. And then you have to integrate sigma with respect to the Brownian motion. And then you always have to have a gradation term. Minus 1/2 integral from 0 to t of sigma u du. Right. Here, this b here, if you want, you can put a q up here because it's going to be under that risk neutral measure. But this is a there's no dt term here, so there's no dt term here, so this is already under the risk neutral measure. These are risk neutral dynamics. So we have a solution, and it's customary to call what you have in here inside the exponential. This is what we'll call the return. This is the return process, and we'll call it RT. It's given as that integral sigma u dbu q minus its credit variation times 1/2. And then we'll see that dRT, let's throw away the integral, so I'll get sigma t dBtq minus the correction term from Ito's lemma, 1/2 sigma squared dt, right? And one thing we talked about last time is that we need to have, if I want to have a macro process, I need to have the drift and the volatility of the right-hand side just being a function of the left-hand side. And we see here we have sigma. So this thing here, this is, while R is not Markov, we often have that R paired with sigma is Markov. And this is going to be the case. This is going to be the case in Heston. It's going to be the case in Stein and Stein. So let's write down what these models are. So you can see the way that it's written down here. Our equity model has two securities, right? There's a bank, and there's a stock. So the bank is very simple. It just has a constant value throughout time. The stock, the only unknown quantity here is this sigma. That's the volatility. So let's try to write down some models. So of course, if we do Black-Scholes, then sigma t, this is just a constant. So that's kind of the simplest case we have. Or you can make it or slightly more general. You can have sigma t. This is a function of time for a function beta of time. Again, the key to go from here to here is this is just a note. You know that the stochastic integral, if I integrate, say, a function like this one with respect to Brownian motion, if this is a deterministic function, then this is going to be normally distributed with mean 0 and variance beta squared in here. Whenever beta is non-random, right? That's what we call deterministic. Have you guys seen a result like this one in your previous stochastic calc classes? Sherry says that you've seen this in Math Finance too. That's great. So, and then just a warning. If beta is stochastic, it fails. And just an example, if I took beta of t to be just a Brownian motion, then if I'm looking at the integral from 0 to t of bu dbu, that was one we had last time, but that came out to be a half times bt squared minus t. And this is not normal. This is not normally distributed. Right? In particular, it's bounded from below, but this thing here is bigger than 1/2 minus t. Right? So you have a random variable which is bounded from below. There is just no way that can be normally distributed. Right? So if you move from a deterministic function into a stochastic process of time, right? So a deterministic function of time, if you replace that by a stochastic process, then this thing here is not true. And you can see it too, if you look at the formula, if you were to replace this beta here, say with a B, you cannot do that, right? Then you have a normally distributed random variable with mean 0 and then a stochastic variance. That doesn't make sense. So you have to have a constant here and a constant here. So you cannot put BT over here. This would not work. So this works. You're guaranteed that this works when the function beta is not random. And if you are to move from a typical Black-Scholes where the volatility is constant into something that is slightly more general, you can do that. It's not a you're going to get very similar formulas to the ones that you have for the constant, simply because that stochastic integral of beta with respect to the Brownian motion, this is again normal. So that was Black-Scholes. There are a couple of other, before we get to Heston and Stein, let me just write down a couple, maybe write one more that people care about. There's one of the first stochastic wall models that were developed was by Hall and White. Here's by Hall and White's stochastic wall model. It takes sigma to be geometric Brownian motion. D sigma t is equal to, say, alpha sigma t dt plus maybe eta sigma t. And then over here, what Hall and White did was he wrote WQ, where WQ is an independent Brownian motion from the B that drives the stock, right? Remember, B is the one, that's the one we find in the return. That's the one that drives the stock price dynamics. Okay, so W is an independent Brownian motion. So what they do is they say conditional on the entire path of W, right? So this is this entire path. We'll have that the sigma t is a deterministic function. And we're back in business. We can now go back and reuse this result here. So when we condition on W, this beta here becomes a deterministic function, and you're going to get a conditional distribution that has exactly this mean and this variance. But it doesn't work. This does not work. This does not work. This does not work when W is replaced by, so W in that. So call this star. When W in star is replaced by, so let's say D sigma t is equal to alpha sigma t dt, and then you have your eta. And then over here, we will write like our rho dBtq minus plus square root 1 minus rho squared dWtq. And so here, if you condition on the entire path of W, so now this part here is fixed, but there's still the Brownian motion B in there. So sigma is going to be stochastic. So Hall and White's model, Hall and White's stochastic wall model, has this form, and the user Brownian motion that is independent of the one that drives the stock. But it will not, what they did in their paper will not be extendable to having both Brownian motions down here. And so there is a term called leverage. And the leverage component, so what does leverage mean? This is, if you look at the quadratic variation between the stock, so you have your stock here, ds is equal to s sigma dB. So I'm looking at the leverage between the stock and the volatility of the stock. So that's the cross variation. And if I compute what this is, so I'll take S sigma from here. And then if I look at the model down here, the leverage component will be an eta, then there'll be a sigma squared, and then there'll be my rho dt. And so empirically, leverage is negative. I mean, not always, but this is often. Not always. So very often leverage is negative. And so you see the problem with the stochastic wall model of Holland-White is that rho would have to be 0, right? This one here is more general. And if I want to get the more general simplified to the star one, then I take rho here to be equal to 0. And so you see when rho is equal to 0, this term here vanishes and you get 0 leverage. So in Steiner's, in Holland-White's model, so Holland-White's original uses rho equal to 0, and that implies that there's 0 leverage. And this is problematic. This is problematic from an empirical point of view. If you guys are interested, we're not going to be working. We are going to be working a little bit with data, but not too much. Let me see if I can find a good book that will take you through some of this. Hang on a second. This here is a book that was very, very popular when it came out. It's called the Volatility Surface, a Practitioner's Guide. And it's written by Jim Gathrow, who runs a master's program out of, it's up here on the north coast, northeast coast. I forget what part. You can look up Jim Gathrow. And if you're interested in leverage, so if you're interested in these sorts of empirical, if you're interested in these sorts of empirical properties that you might want to have in your model, this is a place to look for it. You can see, like, he has discussions. Why do we need to have jumps? If you're looking at this Heston model, what kind of parameters should go into a Heston model? And you can see here, he's also talking about characteristic functions. This is what we're going to be doing next. So this is a cheap buy. It's like 20-30 and it's pretty well written. For those of you that want to do projects on equity modeling, this is a good source to have. It's not very expensive, and it's quite an easy read. Anyway, all this is to say that Holland-White's original stochastic wall model, what the analysis that they do in there, and this particular trick that they use, it won't work if you want to have this negative leverage. So then let's move on to models that we're perhaps a bit more interested in. So Heston's Vol model, this is probably the most famous one. We talked a bit about it last time. Let me write it again. So this model, sigma t, is defined to be the square root of Vt. And Vt is this Feller process. So you'll have a kappa theta minus Vt dt plus, and then you get this volatility of the volatility. So dVt, this is kappa. So this is an affine function of V, and then you have your beta, you have your rho with respect to the Brownian motion that drives the stock, and then square root 1 minus rho squared. Right, so the reason we use this decomposition here is because this here is another Brownian motion. So if we want to compute leverage again, we could compute the cross variation between for example, between S and I think it'll be easy to compute it between S and V. So it's not quite leverage, because then you would have to have had have to put sigma here. Here I'm putting like sigma squared. It just makes it a little bit easier. And you can see I'll get ST, and then the volatility of S, that was sigma, so that's a square root V. I'm going to get V here times a beta times a rho dt. And so this beta here, this is probably going to be negative if you want to get this negative leverage, right? S is positive, V is positive, rho is a yeah, I guess you could have rho to be negative as well. So I should say rho times beta, that's what we want to have, negative. So this allows us to do this empirical, to capture this empirical feature. Of course, Black-Scholes model doesn't capture any of this, right? The cross variation between the stock in Black-Scholes and the volatility, which is a constant. I mean, that cross variation is of course 0 in Black-Scholes. So Black-Scholes doesn't capture any of this. So here we're just talking about what kind of things we might be interested in capturing. So this was Heston's model, and then let me write down Stein and Stein here at the end. Stein and Stein. Stein and Stein says that the volatility is an Ornstein-Uhlenbeck process, right? So this one here, this is Feller. This thing here, this is Feller or square root or CIR. This particular process has lots of different names depending on where it's being applied. Feller was the original researcher who studied this and proved the existence. The square root process, that's because we have a square root over here. And then the CIR process is because in fixed income, Cox, Ingersoll, and Ross, they were the first ones to figure out what zero coupon bonds would look like in such a model. And this is exactly what you guys are doing in one of the homeworks. Right, so we're down to Stein and Stein. So this time we're going to have an Ornstein-Uhlenbeck process. This is an Ornstein Uhlenbeck. An OU process. It has the form same drift. And instead of having the square root here, it just has the Brownian motion as before. Right, and so if we were to look at the cross relation between S and its volatility, we would end up with S sigma that's coming from the stock, right? And then you have beta rho. And this time is problematic because sigma here, and once the Lundberg process, this is Gaussian. So we cannot just choose these constants to have the right sign. Sigma t here is Gaussian. This one here is Gaussian. This one here is Gaussian. Whereas the one we have up here in the homework, you've been asked to figure out what the distribution of filler process is, and you have found that this is a non-central chi-squared. So that means that it is non-negative. And this one here is Gaussian, this is real valued. This one here was non-central chi-squared. So in particular, this is positive Gaussian, this is real value. So you can see, if I wanted to sign the cross variation, that was fairly easy because I just have to, I know this is positive, I know that's positive, but this part here, I just have to choose the right sign. I'm going to get the right sign of everything. Down here, I can't do that because S is positive, but sigma is real valued, so it could be both positive and negative. So I cannot just choose these coefficients here to get either positive or negative process. So again, another advantage of Heston's model. Are there any questions up to this point? Right, so the next homework is really about these two here. I mean, the reference point is, of course, always going to be Black-Scholes. The reference point is always going to be the model over here where beta is a constant. But then the main stochastic wall model is Heston, so we're going to be playing with that. But academics, they also care about Stein and Stein, so I put a problem in there about Stein and Stein. So what I'm going to show you next is how to use characteristic functions to price options in these two models. We're going to switch over to a derivative pricing in these two models. So we're going to look at option pricing using characteristic functions. In these two models, I don't have a good grip on what the density is, at least not a priori, but what I'll show you now is how to compute the characteristic functions. Right? So the goal is to compute the expectation of, say, if it's a call, it's st minus k positive part, right? We recall here that r is equal to 0. You want to compute it with a non-zero r. You just put that factor out here. Okay, so that's our goal. Using say Heston's model. So you have your sigma again would be the square root of Vt, and Vt has the form from the previous slide. So let me write it down again. This was beta root Vt rho dBtq minus root 1 minus rho squared dWtq. Okay. And so if we had known the density function, we could write this out. But ST is quite complicated. Indeed, ST has this form. like ST has this form, right? So it has this return in there, right? So recall that so S capital T, this was E to the RT, right? That was the return. RT was equal to that was the so it was the sigma T dVTQ minus 1/2 sigma squared. R0 was 0, so we can insert here what sigma was, that square root. And then you get your VT here. Right, so right off the bat, we'll note here that, what will we note? We'll note that V is Markov, because if you look at V's coefficients on the right-hand side, they are just functions of V. This is constant, this is constant, this is constant, and that's constant. So V is Markov. R, that doesn't work because on the right-hand side, we don't have coefficients that are just functions of R. There's a V in the middle. VT is Markov, RT is not Markov. And if I put them together, so now I look at these two simultaneously, and that means that the right-hand sides, they can now be functions of both V and R. And that's okay because here I have V, here I have V, here I have V, and here I have V. So this part is Markov. And this is going to be important for us when we do the PDE. When we find the PDE, we always need to have a Markov process. Otherwise, we'll be missing out on variables. Okay, so how are we going to go how are we going to go about our business? We need to compute this expectation up here. All we have so far is the dynamic, the dynamics of Q of V and characteristic functions. Okay, so we need to bring characteristic functions into the game. Okay, so maybe we should start by, let's start by breaking this expectation here into two components. We've done that in Black-Scholes. So let's do that again. This is the, when you look at Black-Scholes formula, let me just pull it up so you can see it. If you look at Black-Scholes formula, just pull it up. So Black-Scholes formula said 118, just flip to 118. See, when you compute, so again, just put R to be 0, right? So this is exactly the expectation you're trying to compute, but in a more general model. What you're going to get is you'll always get these two terms on the right-hand side. So you'll get n of d plus and then n of d minus, and there's this minus a k on the second term, and the first term has this S0 on it. So you should see that this difference here, you're not going to get something so nice with n here, but you're still going to get the same structure in these more general stochastic Born models. So let me show you how to do a more general version of what we have here. You will not have n, but you will have these two terms. You'll have something else than n over there on the right-hand side. Let me show you how to do that. So, so that's the first order of business. We will write this expectation, the one we're trying to compute. We will break it up in two things. So the plus operator, I can replace that by an indicator. So I have st minus k positive part. So I can eliminate the plus by putting in an indicator for when we are in the money. So this is when st, this is a call, so this is when st is big. So that did that. Then what I can do next is I can break it up. So I'll get here EQ, then I'll get ST times that indicator. And then I get the minus K, which was the nice one, and then the expectation of an indicator of ST bigger than K. So you can start to see now that different structure we had in the Black-Scholes formula is going to continue to hold here. And the next order of business is what? Then I will take the constant S0, I'll put it out there. And because it's a constant, he can go in and outside the expectation. So then I'll put the constant in here. And then I'll have the indicator. And over here, I didn't do anything. I just multiply and divide by the same thing. Over here, we'll have a minus a K. And then the expectation of an indicator, that's going to be the probability of the set. So I have that. So now why did I do this trick here? Well, we need to recall that there's something called a Radon-Nikodym derivative. For those of you that have taken my previous courses, you will have heard me talk a lot about Radon-Nikodym derivatives. Right, so we have a Radon-Nikodym derivative. This is a random variable. This is a random variable which is positive, it has expectation 1, and so on. So let me write that down. If I take ST over S0, this is positive, it's strictly positive. If I take expectation of it, expectation on the Q, then what will I get? Well, this object here, remember the interest rate is 0, so this object, S, is a martingale. Those are the risk-neutral dynamics. So it's a martingale, so what I'll get here is this will be S0 over S0, this will be 1. Right, so I have a valid change of measure. This is a random variable that is positive and it has expectation 1. Right, so I can define a new measure. Let's call it Q tilde. dq tilde dq, we're going to define that to be simply just ST over S naught. And then to use Gisanov, for those of you that are currently in 622, have you guys covered parts of Gisanov theorem at this point? Sherry says yes. Okay, so we'll just go full at it. And those of you that had me in 485, we also use Gisanov's theorem quite a bit. So to use Gisanov, so Sherry, you have to bear with me if I'm using slightly different words and different letters to symbolize. It's exactly the same theorem as the one that you're used to here in this textbook. So it might look a little bit different, but it's exactly the same. So to use Gisanov, you need to compute the conditional expectation. You need to compute, and now we're working on the Q. So you need to compute the conditional expectation of the Radon-Nikodym derivative. And then you need to take the dynamics. And then you need to be able to write them. And our textbook here favors a sign convention. So let me stick to that sign convention. Let's just double check it. I once told years ago, I was teaching a class like this one, and I said, the sign convention is not important, and it did really backfired. Then students started throwing away all the signs. So the sign convention, it is important. So let me look up what it says. Gisanov's theorem, this is page 210. Let's just get the sign right. So our textbook, you see here is the conditional expectation. This is what is needed. And then you flip over to Gisanov's theorem in one dimension. The thing that's important here is the dynamics of that conditional expectation, dz, and you have to write it with a minus sign. And then this theta here, theta, this is going to be the market price of risk. So you have dz is equal to minus, and then the c times something, and then the Brownian motions. So for us, what that means is this here is our CT. We got to be able to write it as a minus, and then the same thing. times something. And however many terms we get here depends on how many Brownian motions we have. Excuse me. However many Brownian motions we have to list them over here. We're dealing with a Heston model, so there are two. So we have two market prices of risk. We will have, say, a theta B, and then we'll have the Brownian motion, and then we'll have another one. We have a D on the left-hand side. We're going to have D's everywhere. On the right-hand side, there's a D there. There's a D there. Very good. These two guys, these are called market prices of risk. This is the market price of risk associated with B, and this one here. This is the market price of risk associated with the other Brownian motion. So we always have the same number of market price of risk as we have Brownian motions. So we need to compute the dynamics of the conditional expectation. I need to figure out what these two here are. This is what goes into Gisano's theorem. And, so let's work out what the conditional expectation is. I need to write the conditional expectation as minus the conditional expectation times something. Okay, so let's work out what it is. The conditional expectation of dq tilde dq given if t, well, we use the formula. It's st over s0. So it's st over s0 given if t. And st here again, this was a martingale. So this is st over s0. This is where we used this equality sign here. This uses that st is a q martingale. So now we can compute the dynamics. So we take d of both sides, d eq this is equal to, well, S0 is a constant, so this is 1 over S0 dst. And then I'll plug in what dst is. Go back here, take dst, the formula for dst, just copy paste what we have here, put it over here. So this will be st sigma t dbtq. And now we recognize that the first part, this is exactly the conditional expectation. So we have the conditional expectation of the random equilibrium derivative. That was that part. And then we have our sigma t dbtq. And then we can use, we can now read off, we have that d is equal to the same thing, and then we have a sigma. And what do we see is, well, we see that the W market price of risk is 0. And then remember the sign convention, there has to be a minus out here. So we're going to get that theta B is equal to minus sigma. So theta TB, this is equal to minus sigma T. And the other market price of risk, this is equal to 0. Now we can use Gisanov's theorem. So Gisanov ensures, and what does he ensure? That we have new Brownian motions under the tilde probabilities. You'll be given as the old one, and then plus the market price of risk, right? So that's where the sign convention becomes important. So when you look up, Gesanoff theorem, it was 118. No, it's not 118. Gesanoff theorem 210. Look up Gesanoff theorem. You look up Gesanoff theorem, it's down here in the bottom. This is where the sign convention is important, because if you have a minus sign here, if this comes to the minus theta, then you have to have a plus sign here. If you let go of the minus here and put a plus, then you have to put a minus over here. These come with opposite signs. So you get the new Brownian motion by taking the old one and adding the market price of risk. And you want to add the market price of risk. So in our case, because of the sign, you're going to subtract sigma. And for the other one, for the W, there was a zero market price of risk. So that Brownian motion is just the same as the one you had to begin with. There's only going to be a correction made to the B Brownian motion. Okay, so long story short, we can now finally return up here and work out what these two terms are. So then, this gives us that the expectation we are hunting is t minus k positive part. You can really work this out quite explicitly as S0. And then you have an expectation now, but instead of having it under Q, you're going to have it under Q tilde. You absorb this random variable into a change of measure, and you get ST bigger than K minus K Q ST bigger than K. And as before, right, an expectation of an indicator, and this is exactly the same as the probability of the set. So just look at how similar this formula is to the Black-Scholes formula that we had up in that exercise. Let me pull it up one more time. These are the two formulas that we're comparing. You have S0 times something. Okay, we have S0, and then we have this probability. Then you have minus K, so R is 0, so there's no exponential. You have minus K, and then you get another probability here. So it's quite similar. The only thing is you have to let go of these n's and put these probabilities in there. And thanks to Gesanoff, on the Q, we have one set of dynamics. On the Q tilde, we have another set of dynamics. So we should also say where, so if you write down the formula for the dynamics on the Q, these are Q dynamics. These are Q dynamics. And if I want to write them down in terms of Q tilde, then I'll have to write ST sigma here. Then I'll use Gesanoff theorem. Gesanoff theorem. And he says that if you want to put in the Brownian motion under the tilde measure, I have to correct the drift. But this guy here is equal to that one. And then I have to add. So I'm going to get here, this is ST sigma t squared dt plus ST sigma dBt Q tilde. These are the Q tilde dynamics. And in particular, if you were to look at we were to look at the returns, so the returns, this here was, these were stock price dynamics. So the returns, this would be DRT, DRT. So this will be my sigma dBTQ. That would be the return dynamics under Q. And likewise, if you were to write it again, these are Q dynamics. Write it out here. Then if I were to write it over in terms of the Q tilde, I would replace the Brownian motion on the Q with the Q tilde Brownian motion and then do the correction term. I need a sigma. And then I have minus 1/2. And now I can ease it up. I'll get sigma t and then plus 1, so minus 1/2, so it becomes plus 1/2. So you see the difference between the Q dynamics and the Q tilde dynamics are minor, right? It's just a plus sign and a minus sign. Right, so that's the big difference. Instead of having a minus here, you have a plus here. Any questions so far? Any questions up to this point? Are we all good? Right, so what we need to do then is to compute these two quantities. So it all boils down to the price and option. So to price the call, we need Q tilde of ST bigger than K, which is, of course, if I want to write in terms of a return, I can write this here as S0 e to the RT bigger than K. And we can move it over on the other side. So we'll have log K over S naught, and then you have RT here. So we need this. So that's one thing we need. And the other thing we need is Q of ST bigger than K. And of course, you can write this just the same. This will be Q of S0 e to the RT bigger than K. And this would be Q of RT bigger than log. Okay, so I need these two quantities. I need to be able to compute what this is. I need to be able to compute what that is. And that's where we use characteristic functions. So here the key to do this, we'll use characteristic functions. So we'll use characteristic functions. But we know that, so the characteristic function, this is my phi of t. This is e to the I t RT. So be careful here. This is a typical place where mistakes are made. This one here, this is not time. This is my characteristic function. And then I'll get back the probabilities over here. I'll get then that Q of the distribution. We have to flip this thing here. So this is going to be what would be R T less than what should we call this, X. Maybe just write it out, log K over S naught. I can get this thing back. I'm interested in this quantity, so I can write Q of RT bigger than log of K over S naught. I can write this as 1 minus this quantity. And then I can write this as, this is where we're using the inversion theorem, 1 minus, and then we have to remember what the inversion theorem says. This is from an earlier lecture. This is 1/2 minus 1 over pi, an integral from 0 to infinity. And then it was the imaginary component of e to the minus it. So this is, you run it the opposite way. And then you evaluate it at log of K over S naught. That was the point we're evaluating it at. And then we need to phi, the characteristic function, phi of t. And then you divide here by t, dt. So provided that you can figure out what phi is, you can calculate this probability here by performing this integral. And of course, you have to do a similar thing for the Q tilde probability. Similarly, Q tilde of RT being in the money, so log bigger than log of K over S naught. Like this can be found using the same formula, 1/2 minus 1 over pi, integral from 0 to infinity, imaginary part of e to the minus it, and then this log. And then the different characteristic function, phi tilde, where the characteristic function, like this characteristic function was computed on the Q, you need the characteristic function on the Q tilde. So provided that you can figure out what these two characteristic functions are, then you have the formulas. You have an integral here, time integral, and you have time integral for the other one. So if you know what these two characteristic functions are, you can figure out what these two probabilities are, and then you can figure out what the needed expectation is. If you don't remember where these formulas are coming from, you need to go back and look at the lectures where we proved formulas like this. There was also a set of homework problems related to characteristic functions, and this is where the reason we've been doing so much about characteristic functions has been that this is what goes into Heston's model, because in Heston and Heston, so in Heston, in Heston's model, these two characteristic functions, phi and phi prime, are available in closed form. And in Stein and Stein, they are, and in Stein and Stein, they are available up to a couple sets of 3 ODEs. So what I'll take you through now is how to derive these characteristic functions in say Hessen's model. Any questions so far? Any questions so far? Are we good? So let me take you through how to get the characteristic function in Hessen's model. So this is quite similar to last time when we were talking about replication. So let's do Hessen now. Hessen's model. So we will start out by recalling the dynamics. So we have our dVt. This was this one. We've had it a few times now. And then we have our dRt. This would be sigma t, and then that Brownian motion. Minus 1/2 sigma squared. And sigma was the square root of Vt. So let's compute the first characteristic function, the phi one, and let's see what we get. So let's try to compute. E. Let me switch the index out here because otherwise it's going to be a disaster. I mean, instead of T, I'm going to call this for A, and then R capital T. So we have to come up with some sort of a very good guess here. What is this equal to? And the way that we do this stuff is by conditioning. So we look at a martingale, just like last time, a Levy martingale. This time it's going to be valued in the complex plane. We're going to be looking at a conditional expectation. So this is why I'm switching A out with T, because I like to use little t as time. So this here is a martingale, it's complex value. And we're going to make a guess on what this thing looks like. I'm going to make a guess on what this thing looks like. And let me write this here as E. And then what should we put in here? Well, the terminal condition is going to be IA. So let me try to put an RT here. But then I know that R is not Markov, right? We also have to keep track of V. So let me put in some deterministic functions. Let me say A of t minus t minus a B t minus t times my V. So this is our guess. Sometimes people call this a conjecture. And Germans call this one Ansatz. So now let's check it. So the first order of business is what happens when I put T to be capital T. Well, the left-hand side becomes e to the IA R capital T, and the right-hand side becomes EIAR capital T, and then there's a minus A0, there's a minus B0 times V capital T. So if I want this to be the same, we're just going to choose these deterministic functions, initial values, to be 0. So that'd be good there. Now let's go to earlier times. This is where the martingale property becomes important. We're looking at computing these conditional expectations under the risk neutral measure Q. So let's try to look at that. So we're going to apply E2 and set dt terms equal to 0, right? Because it's a martingale, so there should be no dt terms. So we apply E2's lemma to the right-hand side. So let's start by computing some derivatives. We need a bunch of derivatives, right? So the function I'm looking at is f of t, r, and v given by e, I, a, r minus a, t minus t minus b, t minus t, b. And so to use each lemma, it's two-dimensional. So I have lots of derivatives to compute. We need a time derivative. So let me call that just f1. Save a little bit of space. Let's call this f1. Well, it's an exponential, so I'm always going to get the exponential back. So this is equal to f times time derivatives. So I'll get here time derivatives. There's no t here. There's a little t there. So I'm going to get an a prime t minus t. Then there's a minus and a minus to cancel out. Plus b prime t minus t times v. Okay, so that was the first one. Then I need a derivative with respect to r. So again, I'm going to get f, and then I'm going to get ia. And I'm going to get f22. This is fia squared. This is minus fa squared, right? I is equal to the square root of -1. Then I need derivatives with respect to v. So this is f3. I need to look for a v. There's a v over here. There's a v over here. So I'll get f again times minus b. Then I'll do f3, 3. This will read as f times b squared. Excuse me. And then it'll be, the last one will be the mixed terms. I need an f23. So I'll do this one. So I get ia times, and then the derivative of f with respect to v is going to be minus b t minus t. I think those are all my derivatives. And then we plug it into Ito's formula. Ito says that if I take df, I will get I'll get f1 dt plus f2 dr plus 1/2 f22 and then the credit variation of R. Then I have a V term, F3 dV, plus 1/2 F3 credit variation of V. And then I need the cross term. I need two of them, so I'll get F2 and then the cross variation between R and V. So it's a bit long, and the reason that it's long is because you have your macro process is two-dimensional. It goes from normally just being 1, 2, 3 terms to being 1, 2, 3, 4, 5, 6 terms. Right? So it goes up quite a bit. And then the next step is plug everything in. You're going to get a big F outside. And then we start out with the time derivatives. So A prime plus B prime V dt. That was the first one. F2, this was IA, and then you need a dr. Okay, dr, we know what that is. Dr was all the way up here, right? That was our dr. So this one is root Vt dBtq minus 1/2 Vt dt. That was our F2. And then we have an F22 times 1/2. Okay, so F22 was minus 1/2. F is outside, A squared. And then we need the credit variation of R. Okay, credit variation of R. Forget about the dt terms. We square the integrand here. This is going to give me Vt dt. So that was that term, and that term. Then we left with F3. Okay, so what was F3? That was minus B. Minus B. Minus B, and F is still outside. And then dV, this was kappa theta minus Vt dt plus what's it here, beta root Bt rho dBtq minus plus 1 minus rho squared dWt. I need one more parentheses over here for 2. That was minus B, that was this guy, and then you need 1/2. You need 1/2 F3. What was F3? It's up here. This is B squared. The credit variation of V. Okay, it's going to give me a beta squared Vt. And the credit variation of this thing is just dt because it's a Brownian motion. And then finally, we need the cross variation. This is minus IAB. And then the cross variation between R and V. Okay, so let's look at the cross variation between R and V. We only have to worry about the Brownian motion terms. We only have to worry about the B Brownian motion. So on one hand, we're going to get a beta, and then we're going to get beta times V dt. And unless I made a mistake somewhere, which I probably did, this is the mess that you get. Right, and so what you want to have here is you want to have a 0 dt, and then you want to have some martingale terms. You want to have the martingale terms. What are the martingale terms? Well, there's one here, IA root Vt dBtq, that was one term. And then there's some mess over here. There's a minus a B, beta root Vt, and then this is rho plus root 1 minus rho squared. But it's the 0 dt that's going to give us the restriction. So what we do now is we just, how do we get all this stuff up here? We know it's going to be a martingale, so there has to be a 0 dt term. We have to compress all this stuff in such a way that we get a 0 dt. And the thing that's magic about these models is that when you look inside, the drift is affine in V. You only see either something that doesn't have anything to do with V, or you see linear terms in V. Let's try to explore that. So the drift in df over f is affine in Vt. So this is going to give us two terms, right? It will give us the Vt terms, and it'll give us the constant terms. So let's try to collect all of those. So we have A prime, this is constant, so I should say constant. This one here is the remaining. But you're not constant in T, you're constant in V. We have A prime goes down there. Then I'll have B prime goes up here because it's multiplied onto BT. And then we move over, what do we have here? We move over, what do we have here? There's a Brownian motion term, forget about it. We have minus a half V. Okay, so that's multiplied onto IA. Okay, so that's that guy. We'll just mark them up as we go along so we don't miss any. We got this one, got this one. This one was moved down, this one was good. And we down here, there's again a V term, so we're going to get minus 1/2 A squared. And this guy's gone. And over here, there'll be a minus a beta, no, minus a B kappa theta. That was the first part. And then you have a minus and a minus. This is a plus B kappa. Then we have the Brownian motion terms, so you're all good. And then the last two terms, this is where we pay the penalty. There's a square here on the B function. This is where the Riccati equation comes up. 1/2 B squared beta squared times V minus I A B beta. But we want this to be 0 and we want this to be 0. And so we see that the B equation, the B ODE, only depends on B. B prime ODE only depends on B. So this is one of these Riccati that we talked about before. So that's one thing to note. And given B, you get A by integrating. So you get that A of t is equal to A of 0 plus an integral over A prime right, and A prime is exactly that. A prime is exactly kappa theta B of U du. Right, so as soon as you know what B is, you can get A by integrating. So all you're stuck with is this long ODE for B. So can you solve this long ODE for B? If you can, you have everything in closed form. And already in your homework number 3, let's just have a look at your homework number 3 then. This year's homework number 4. See if I put in the solutions in there somewhere. There we go. You'll see here, that is that exercise that that we're basically doing now. We're doing Heston's model. We're doing Heston's model, and you get your system of equations. C2, this is a time derivative, and the closed form expression is given here. This coupled ODE system has an explicit formula as its solution. So now you have at least one of the two phi functions, one of the two characteristic functions. You have it in closed form. So here you can see homework for the explicit solution. Are there any questions on this part? And the only other part that is left is this phi tilde, right? We need to do the same thing for phi tilde. We need to calculate phi tilde. So let me recall what that is. That is the expectation under the tilde measure of e to the IA RT. Right. So what we will do now is we will make a similar guess. We will guess a similar form for what we had before. We'll have A and B. They're going to be replaced by A tilde and B tilde. This here is going to be exponential of I. Right, so we calculate the conditional expectation as before, and we're going to make the ansatz, so the guess that this is EIART, and then the two functions, they're going to be different, but the way that we find them is going to be similar. And the only difference is when you look at the dynamics of R and V, those are going to be different, right? But for the dynamics, but now use the dynamics. So what was it? DRT. There was a correction term. If I write down the Q dynamics first, this was sigma T dBTQ minus 1/2 sigma T squared dt. And remember, the difference between the Q and the Q tilde would be that sigma. So instead of, if I want to put a tilde here, I have to replace the minus sign by a plus. And likewise, if I were to write down the dynamics of the volatility, this would be kappa theta minus Vt dt plus that beta root Vt, and then the two Brownian motions, rho dBtq plus root 1 minus rho squared. And again, remember W stayed the same, but this guy, he gets changed a little bit. He gets changed a little bit. So let me write it out. We have the first part, right, and then you get rho, but instead of that Brownian motion, we need the other one. And then we need to remember the connection between the two. We need to remember the connection between the two, so we flip back to when we had Gesana's theorem. Flip back to when we had Gesana's theorem. Gesana's theorem says that the old one is equal to the new one plus sigma t. Right, so if I want to replace the old Brownian motion by the new one, I need to add sigma, which in this model here was square root of Vt dt, plus, and then the new W Brownian motion is just the old one, so there's no change there. course, and I can now again find a decomposition. So I have drift and I have volatility. Inside the drift, I'll have kappa theta minus VT, and then there'll be new terms popping up. There'll be a beta and a rho, and then V, because square root of V times square root of V is going to give me VT. So that was that term and these two, yeah. And then the volatility is going to be beta root VT rho dVTQ plus square root 1 minus rho squared d double VTQ. So you see, there's just going to be a little change in the drift. Instead of having the drift just be kappa theta minus V, there's going to be this beta rho in here. But again, it's going to be linear. The drift is again going to be linear in V. And the volatility is going to have the same form as before. Now these ones here are tildes. So then you go through the same calculation as before. There'll be some changes, but not that many. This term here is going to appear a few places. The same thing, there's going to be a sign change because before you had minus 1/2 sigma squared, now we're going to have plus. And that will allow you to calculate the phi tilde using these closed form solutions. And now you have phi and phi tilde in closed form. You use the inversion theorem, and you're going to get the prices coming out of the Heston model in more or less closed form. Okay. Are there any questions or comments here? This first part of today's lecture, it really used a lot of things that we've done before. It used a lot of these characteristic functions, and then it used this material from last time when we were talking about how to compute expectations using martingales and PDs. Are there any questions or comments? Okay. If that's not the case, then I propose we take a little break, get back together here a little bit after 10. And after the break, we're going to do copulus. So we're going to switch over to something very different than these continuous time models, back to simulation, and talk about how to simulate copulus. Okay, I'll see you a little bit after 10.